Number 15 usually gets people because there is an x-intercept. Did anyone say none? It's large, but did you find it on your own or did you have to use the answer key? That's the question. Okay, so for those of you who use the answer key, we want to make sure we could get an answer like that on our own. So negative cube root. Does anyone know how to actually get the cube root on their calculator screen? Yes, how do we do it? Math button. So before that, I'm going to type my little negative. If you're starting off with a negative in front that's flipping it, you're not using this. This is a minus in the middle of an equation. You have to use this negative, so we're doing negative. Okay, and then you guys said we hit the math button, which is over here. So the math button on the left, third one down, math button. All right, and then which one? Number 4. All right, cube root. Negative cube root of x, and then what? Plus 17. So what has happened to this graph? Somebody tell me the transformations. Yes. Reflect over x and up 17. Okay. So I'm going to go ahead and take my window. I know it's been shifted up 17, so I probably am not going to be able to see very much of it from a normal window, negative 10 to 10. Okay. So I'm going to walk you through your process. Hold for just 1 second. I'm going to take my y max, since this whole thing has been shifted up 17. I'm going to take my y max and I'm going to make my y max 20 window. I'm going to take my y max, make my y max 20, so that I can see this on the graph, because otherwise I'm not going to be able to see very much. Okay? And the reason that I did that is because it was shifted up 17. So y max is the up part of the graph. Everybody good so far? Following along? Okay, hit the graph button. I can actually see it right there at the top. All right. Now, this is the cubic graph. That's the sideways one. It goes to the right for like forever. It's going to go to the right forever. It's going to the right rather slowly. So the thing about x-intercepts is that you can't just tell the graph, second trace, okay, look for the x-intercept, and say, oh, left bound is 0, right bound is 5,000. I can't tell the calculator to do that, because what the calculator does is it treats your x min and your x max from your window, it treats them like a domain. So if your window does not have that x min and that x max, it will not let you plug those numbers in. So I just tried to do 0 to 5,000, but my window was negative 10 to 10, okay? I'm trying, right now, I'm about to try to plug in a number that's not in my window. My calculator will not let me do it. My calculator will only let me plug in numbers that are on that window, okay, for x. For outputs, it doesn't matter. If the input for x is there, the calculator will let it have the output that goes along with the x value, okay? So if I want to have a bigger x value, it's got to be in the window that I have. Does that make sense? Yes? Okay. James, what were you going to say? That was it? So basically at this point, we start doing guess and check. As far as like what window should be happening. So that's what I did when I first made this problem and I wanted to find what the x-intercept was. I wanted to give you guys a problem like this because I wanted to make sure that you guys recognize just because I can't see the x-intercept doesn't mean that the answer is none. Does that make sense? It's going to keep going down. Eventually it's going to cross that x-axis. It's just not going to be at a convenient place for me to write the answer. So I can see it's going down. If it's on the right side, that is x max. X max is what I need to make bigger for more numbers to the right. So when I was doing this on the answer key, I was like, okay, I'm going to be really extreme here. I'm going to make it go to 50. And then I graphed it, and I was like, oh no. That's not very close. And so then I was like, okay, I'm going to be real extreme here. I'm going to make it 500. And then I was like, oh no. I did a bad thing in writing this problem because it's going slower than I meant for it to go. And so then I changed my window to 5,000. And then finally it crossed the axis. Barely. Okay, so see how, like, I'm pretty sure it's crossing, but I can't even see where. You guys notice that? I'm gonna do, for my left bound, right bound, I'm just gonna do like 2,500 to 5,000 and hope that it's gonna cross, okay? And then if it doesn't work, I'm gonna make my window bigger. Do you guys see how the strategy that I'm using here? Okay. Say it again. Yeah, and then you'd really be able to see that it crossed if you did 10,000, yeah. So I'll do second trace. For 0, for my left bound, I'm going to do 2,500. For my right bound, I'm going to do 5,000. Guess. And then there we go. 4,913 for that very, very frustrating problem. Yeah. So your calculator can do it. You just have to be smart enough to guide your calculator to the window that's going to work to make it happen. Yes. I mean, it can keep going. There's just a point where the graphs can get kind of cumbersome, where it's like, unless you make the window proportioned to the side, to a way where you can see it well, you can set any window size you want, but it might be proportioned so that you can't really see anything. Does that make sense? You can always tell when somebody's made the window big because the axes get really thick looking. That's because the little notches are at 1s. If I were to take the window and change these little notches so that my X scale is not at 1s anymore, if I change it to 1,000s, it's not going to look as thick anymore because now it's 1,000, 2,000, 3,000, 4,000, 5,000. Now it doesn't look as funky anymore. So yeah, in theory, you could make these as big as you wanted. It's just what usually happens, and you'll see this for a student who starts in science class and comes to math class, and then we graph something normal in math class, and they're like, my graph isn't showing up. And I'm like, let me see your window. Oh, it's left over from science class. You had some big numbers in there or something for your scale. That's why. So it's not that there's numbers that are impossible to use. It's usually that like certain numbers just make it really hard to actually see from the proportions what's going on. Does that make sense? Okay. All right, so that was one problem I expected us to have issues with. Let's look at, I think the other ones I thought we would probably want to go over 34 through 37. Yes? Okay. So it says, where does f of x equal g of x? You have two options for how you could answer that question. You could give the x and the y coordinate, but when they ask the question where, technically the only value you have to give is the x value. So when they ask a question like where, that is an x value answer. So those actually cross each other at a very nice point. It's not a decimal answer. It's like a nice whole number. So what is the location where those two things cross each other? -2, -5. So we just say x equals -2. Call it good. Okay. So we have a cubic graph. We have a square root graph. Can you tell which one is the cubic? Is it the dark one or the light one? The dark one. Okay, so that means this one right here is f of x. This one right here is g of x. So they said which one has the greatest x-intercept. By x-intercept they mean, or greatest, they mean like the biggest number. So we have an x-intercept right here. For the square root graph, I can't see the x-intercept. It's off the screen. Which one has the greatest x-intercept? It doesn't ask for what it is. It just asks which one's biggest. G of x. It's off the screen, but so this one, f of x, has a negative x-intercept. G of x has a positive x-intercept that's way off the screen. By default, without even doing any math, I know g of x is bigger just because it's positive. I don't even have to do any work. G of x is greater for sure. Okay. Where is f of x greater than g of x? Do you guys remember, we've done a question like this before. Do you guys remember how we can tell where f of x is greater than g of x? When the y values are bigger. And what does that look like on the graph? When it's above. Okay, so f of x is the dark one. We're looking for when the dark one is above the lighter one, because it's y values. F of x is y values, g of x is y values. So we're looking for when the y values of the darker one is above the y values for the lighter one. Yes?
What about when g of x doesn't even exist?
So it's a good question. You have to consider it, right? Because there's a part of the graph where it doesn't exist. Okay. The other thing, too, is this says greater than or equal to. So we can look at where they equal each other, and that could be a place where we could maybe think about starting our answer. So they equal each other where? So -5 is the y-coordinate where they start. Okay, so it says where, so our answer has to be in terms of x-coordinates. So x equals -2 is where they start equaling each other. Okay, is it to the left of that f of x is bigger, or is it to the right of that f of x is bigger? It's to the right. So if you look to the right, when you compare the two lines, f of x is higher than g of x. And if f of x is higher than g of x, that means the y values are bigger, because bigger y values are higher up on the line, right? So if we look right here, when you have an x-coordinate of 0, this y-coordinate is almost 4, this y-coordinate is a negative number. So this y-coordinate wins, it's bigger. Okay? So f of x is bigger than g of x at the same x value. F of x is bigger than g of x at the same x value. F of x is bigger than g of x at the same x value. So they're equal to each other at -2, and then f of x is bigger, 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 and it looks like it just stays bigger the whole time. Yes?
What about off the graph?
Over here?
No.
Other way, you don't even have to worry about it, because this graph goes down forever, that one stops, so they're never going to cross again. So. You don't have to write it because the question doesn't ask. So let's answer this one, and then we'll talk about that, because it is a good question. So where is f of x bigger than g of x or equal to it? So we're going to start at -2, and then we went to the right forever. So how do we say we went to the right forever? Infinity. Now, based on the way they asked the question, should -2 get a parenthesis or should it get a bracket? A bracket, because it says where they equal each other. You're starting where they equal each other, so that means they get a bracket, because that's where you're starting. What should I put around the infinity? Parenthesis. Now, if it asked a question like where was g of x bigger, then you'd only be able to consider the parts where g of x actually showed up. So if they asked where g of x was bigger, you'd only be able to look at this part, and then where g of x stops suddenly. G of x stops suddenly at the locator point, which is at -6, -7. That's where it stops. You could say from here to here is where g of x is bigger, and then anything to the left of that, you'd be like, well, the graph isn't there, so it's not bigger.
With this question, it asks where f is bigger. Couldn't you say that by default f would be bigger where g doesn't exist?
You can't, so it'd be like, who is taller, this person or this person? You negate the question when you stop comparing two things. Does that make sense? So as soon as you are taking away something to compare it with, then the comparison ends. Yeah. All right. Where are both functions increasing? So look at both of the functions. What do you notice about them if we had a stick figure and the stick figure was walking on the functions? They are both increasing. Do you guys see that? So should I just say both functions are increasing from -infinity to +infinity? Because they're both increasing the whole time. No, why not? Yeah, one of them doesn't start at -infinity. So the dark line does increase from -infinity to +infinity. So for that one, it would be true. But the other one does not increase from -infinity to +infinity. So I can't make a statement that is not true for both of them if I'm trying to talk about both of them. Does that make sense? So if I'm talking about two girls, I can't say they're both brunettes when one of them has blonde hair. Does that make sense? I can say they both have lighter hair if I want to, but I can't say they're both brunettes when one of them has kind of blondish hair. Yes?
say -2, -5, and then 2 positive.
So -2 was the point where they crossed each other. What is the point we actually want to use? -6. Now, so we're only going to use the x coordinate. We're not going to use the y coordinate because when we do, if you guys remember, when we do increasing, decreasing, we only use the x values. We don't care about the y values. So we're going to use the x value -6.
Does the darker line, does that eventually reach -6?
Yeah, it would go. It would reach it like there-ish.
That kills my nerves. But
You didn't like that?
no, because you took us all days. And the
But you
graphs.
wanted to know.
But yes, I understand now.
Okay.
But that hurts me.
Okay. Well, but you want to know, so yes, it would.
Yeah,
Eventually.
Yeah,
Eventually it will. Yes. Okay. All right. Brains are good? Brains are feeling better? Yes. Yeah, let's do the challenge. Okay. What points did you guys use for the transformations? Somebody used 9-3. I like that. Okay. And then what transformations do we do? Not left 3, right 3. Perfect. 3, 4, 7, 12. Okay. And then okay. So right 3 up 2, right 4 up 3, right 7 up 4, right 12 up. Dotted line or solid line? Dotted. It says greater than dotted. Can we plug in 0, 0? Ugh, this has never happened to us before. We can't use 0, 0 because the domain for this graph starts at 3. 0, 0 is outside the domain. So if you look at this whole part over here, no shading. No shading, no nothing over there. It's not allowed because all of those x values are outside of the domain of the graph. We don't even get to touch that part of the graph. That part is off limits, okay? So when we do the shading for this one, we're going to shade above or we're going to shade below, and we have to pick a point that is above or below to determine where the shading is. It doesn't matter what point we pick. I like to pick points that are easy to plug in because I'm lazy. That's why I usually pick 0, 0. So what point would you guys like to pick to be lazy? 4, 1. Let's do it. 4, 1 is right here. Okay? 4, 1 is right there. So we've got 4, 1. So that's 1 for the y value. 4 minus 3 plus 2. 1 is greater than the square root of 1 plus 2. What's the square root of 1? 1 plus 2. What's 1 plus 2? Okay. Is 1 bigger than 3? False. Okay, so 1 is on the underside. This is false. That means the other side is true. So where should we shade? Above, and we can only shade as far as 3. We can't shade any further than that.
Is it possible that both sides can be false if it's a problem with like a greater than symbol or less than symbol?
No, one side or the other.
It's always one side.
Mm-hmm. Good question. There we go. That was a challenge question because it's funky that you can't shade a whole chunk of the graph. That's weird. All right. How was that assignment? Did we hit all the problems we needed to hit? Are there other ones we needed to look at? Yes. 14. So what points do we need to plug in to do 14? -2, -8. It's cubic. What are the other points? 0, 0. Okay. And then what's the first transformation we would do? Okay, so take the y coordinate, change the sign. And then what's another transformation? Left 2. Okay. And then the last transformation is down 1. So 7, 0, -1, -2, -9. There we go. Boom. Shakalaka. Feel free to quote me on that. Miss Rice said. Yes. Okay. What would a sketch of this look like? So it would be like this. Okay. So increasing, decreasing. We put a little stick figure guy in there, and what the stick figure guy is doing first is he is walking down into a valley. Do you guys see that, how he's walking down into a valley? Okay. So he's walking down into a valley, and then he levels off for a second, and then it's very interesting because at the bottom of that valley, then he walks down over a cliff. I don't know why that it's situated like that, but that's what he's doing. Down into a valley, then down over a cliff. That's how it slopes, though. Do you guys see that how it slopes? Down into a valley, down over a cliff, but he's going down the whole time. So how do we write increasing? None. And then how do we write decreasing? Perfect. Okay. Anything else? Oh, good.
Can you touch on end behavior?
Yeah. Is there a specific one you'd like to do the end behavior of? Because we did end behavior for 21 through 24, and then there's end behavior for more of them too. 22? Okay, so 22 is a square root graph. It is upside down. So 22 looks something like this. Can somebody tell me what the locator point is for 22? Because we are going to need that to think about that for the end behavior. So what's the locator point? 5, 6. Okay, so for end behavior, we're going to say, as we look at the left arrow, as we look at the right arrow. Okay, so I drew a little sketch of approximately what my graph would look like. Do you guys see, are we okay with how I came up with that little sketch? Okay. What does my left arrow look like? Yes. Yeah, non-existent. There is no left arrow. So this is where I say for my left arrow, y is undefined. My left arrow is nowhere to be found. Okay? What do I see for my right arrow? Pointing up or pointing down? Pointing down, so I'm going to say negative infinity. So left arrow is Invisible, it's not there, so it's undefined. Right arrow is pointing down. Okay. Is there another end behavior situation we want to do? Yeah. Okay, 21 is x squared. What does that look like? U shape, and it's got a negative in the front, so it's upside down. Okay, so we're going to say, look at my left arrow, look at my right arrow. Okay. Left arrow, right arrow. Is the left arrow going up or down? Down. Is the right arrow going up or down? Down.
How do you tell what the graph looks like just by looking at the problem like really fast?
Squared is a parabola. Cube root is this thing. Cubic is this thing. Square root is this. So I ignore the transformations, and I pick out the little part that makes the different equations different from each other.
Okay. And the locator points, do they have anything to do with the way the arrows are pointing?
The locator points do not, it's the coefficient.
Okay.
So this is a parabola that's normal, right? Normally it would be positive infinity, but because there's a negative in the front, it forced it to go upside down, and that's what made it negative, negative. It would be normal like this. So the first arrow is pointing down. So the left arrow is down. The right arrow is up. So that'd be a positive. Mm-hmm. Yes. Uh-huh. Uh-huh. It's so it's 1, then 8, and then 27. Nobody does the third point. Yeah. Yes. Yeah. Right. The increasing, decreasing part, or the end behavior, or just all of it? Okay. So what shape is 32? What does 32 look like? The snake, yeah, and they actually call it an S-curve. The cubic, they call it an S-curve. So parabola going, half a parabola going up, half a parabola going down. So if we have a stick figure who is walking, it is like the stick figure is walking up over a cliff, and then the stick figure gets to the top of the cliff and then has to walk up out of a valley. You guys see that? Up over a cliff and then up out of a valley. So this is our stick figure. If our stick figure is walking, it is increasing and then increasing some more. Lots of increasing there. Definitely going uphill. So what should we write for our increasing answer? Okay. And what should we write for our decreasing answer? Okay. How should we describe our left arrow? Left arrow is going down, okay. How should we describe our right arrow? Positive, it's going up. All right, let's go ahead and switch gears. What problem from 1 to 6? What problem are we most scared of? 5? 5? 5 because it's a horizontal line? We're scared of a horizontal line? Okay, we're scared of a parabola and a horizontal line? Okay, I guess we can be scared of a parabola and a horizontal line. That's fine. Okay, that's fine. By all means, let's be scared of a parabola and a horizontal line. Okay, parabola, remind me of the points. All right, what do I need to do to the points to draw that parabola? Subtract 2 from the x, so we're moving them all left 2. Okay. So just remember, we're going to very lightly draw the parabola in. -4, 4. -3, 1. -2, 0. -1, 1. 0, 4. Just going to be lightly sketching it. Okay. And then once you sketch it, what do you do? Before you erase, you circle something. What should I circle? I might not have, maybe I picked up on doing this after I made the video. If you circle where x equals -1, so let's draw a circle right here. Yes.
Oh, that's so nice.
Okay. So I circled -1 because that is where I'm going to have to figure out which side to keep. Okay. I am not filling -1 in. Why not? It does not say equals. Okay. Should I keep the left side or keep the right side, and how do you know? Keep left side. Why? Because the arrow's pointing that way. Also because that's what this means. It says less than -1. The number's less than -1 or to the left. The arrow pointing that direction only works if the variable's on that side, so just make sure that if you use that method, that your variable's actually over there. So I'm going to go ahead and make this dark. These are not inequalities. You're not graphing an inequality. This right here is not an inequality, so you don't have to worry about dotted versus solid. Yeah. Okay. And then I can erase the rest. Now, this part here, when it says g of x equals 3, that's the same thing as saying y equals 3, which is just a horizontal line at 3. That's all that is a horizontal line at 3. So this is what we have. A horizontal line at 3. That's what we got. So again, we're going to circle -1. And this time, should we leave it open or should we fill it in? Fill it in. And what side are we keeping this time? The right side. And then we erase the other part. Now, these are called piecewise functions, so they should always pass that vertical line test. You should always be able to put your pencil across and make sure it doesn't touch more than one part. Yep, it's touching both points at the same time, but one is open and one is closed, and that's why it's okay. Pete, how can I help you? Yeah, what's up? Oh no, you gotta do that whole thing. I know. Proofs are so fun, aren't they, Pete? Aren't they fun? Pete is so excited. You're welcome, Pete. Have fun with your math. You're welcome. Have so much fun. You guys, my math too. They had homework. They had homework one night, and they were like, "Oh my gosh, we have homework!" And I was like, "You guys, just wait until next." Some of them have me again next semester, and I was like, "Bless your hearts. Just wait for math 3. Bless your hearts." Yes. By looking at this. See how this one points to the left? So I drew the parabola, and I drew the circle at the number, and then I said, "Oop, keep the left side." And then for this one, I drew the straight line. I circled the number, and then I said, "Oop, keep the right side." Yes. Yeah, let's flip it on the other side and try to find one of these. I think these are a little bit more difficult. So flip to the other side. Let's find one on the other side to do. Yes. No. Kind of. We're talking calculus now. Well, because, so to connect this to what we've been learning, a lot of our limit problems were with piecewise functions. That's why you're recognizing it. Mm-hmm. Yeah, actually, this applies to you guys. So look at this. We talked about the graphs. Remember when we talked about continuous, like you could trace it, the whole thing with your finger without picking up your finger? Can you trace this with your finger without picking up your finger? No, you gotta pick up your finger to trace that. There's a jump in there. You guys see that jump? This is probably the first graph that we've talked about with continuity where like you can't trace it. This is not a continuous graph. We have finally come across the ones where when they ask if it's continuous, you finally get to say no. It's very exciting. All right, flip to the other side. Which one should we do? Number 10? That is a good choice because I'm pretty sure that is the hardest one on the entire worksheet. All right. I mean, it only has 2, but a lot of like symbols, math symbols. Okay, what are the points that we use for absolute value? -2, 2. That's what you meant. It's okay. -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Okay. And then what are we going to do with all of those points? Transform them. Up 1. Up 1 for all of those points. After this, would it be helpful if I wrote all the little charts on the board for you?
Yes, very helpful.
Yes! I mean, that'd be okay. All right. Okay, so there's our absolute value graph. So we've got -2, 3, -1, 2, 0, 1, 1, 2, 2, 3. Lucas, can you do me a favor? Only because I'm assuming you're working ahead. Am I accurate? Yes. Okay. Can you take that empty desk right there at your group and carry it out into the hall for me? Thank you. All right. So we are going to lightly trace this. Liliana, the time has come. All right, while I get Liliana settled, I need you guys to find the spot on the graph where you have to draw a circle. I need you to figure out if you should fill in that circle or not fill it in. And I need you to discuss in your groups like where you need to start erasing, okay? So draw a circle on the graph, figure out where the circle should be, figure out what you're going to keep and what you're going to start erasing. What number are we circling? Okay, Are we filling it in or not filling it in? Okay, and then what part are we keeping? The left side. The part that we barely got to draw. Huh.
Feel anything?
No? The way the killing works is it only counts if it's a conceptual mistake. It means that you made the mistake because you didn't understand something. You'll notice, like, I don't have a baby animal up there for like missing a negative, because you guys don't miss negatives because you don't understand how negatives work. You miss a negative because you just didn't write it. You know what I mean? You just didn't write it down. Yeah, like you just didn't copy it, or your handwriting wasn't great, so you didn't see that it was there. I low-key was going to have one, because the higher up in math, some students will literally get problems wrong because they could not read their own handwriting, and that is an issue. It's not good. It's not good. All right, so we got that part. What are the points we're going to use for the next one? 0, 0, 1, 1, 4, 2. Okay, and then what do we have to do with those 3 points? Two to the x. Are we minusing or adding? Okay, minus 2, minus 2, minus 2. Okay. Okay, I drew it nice and light. This is the part about this problem that makes number 10 difficult for students. Because what I would have said is find -3 on the curve. Do you guys see the problem already? Find -3 on the curve. But Ms. Rice, it's not there. Okay. Find -3 on the curve, and then what part of the curve are we keeping? Everything to the right of -3. So you can't find -3 on the curve because the curve doesn't go that far, but we're keeping everything to the right of -3, so how much of the curve do we get to keep? The whole thing. Does that make sense? No. Just means you get to keep the whole thing, so you can make the whole thing dark, just keep it. So that makes this problem kind of unique. Yeah. We can't put a circle anywhere because the circle would have been at -3, but -3 is not even there. So the one in piecewise functions, the square root does not operate the same way the other graphs do, because it does not go across the entire graph the way the other graphs do. So sometimes, like, our strategy that kind of makes this easy for us is like finding that number and circling it and then erasing the other half. It doesn't always work with square roots because you can't always find the number and circle it. Sometimes you're going to have to like think that one through a little bit more. So that made number 10 a more difficult problem. But the nice thing is, I think that's the only one on the sheet that has a square root. I think the rest of them are all the graphs that are a little bit easier to handle. Okay. As you look at the sheet, are there any other ones that feel intimidating? In the beginning, these are y equals mx plus b, number 1 and number 2, y equals mx plus b. So in case you are having a brain fart, this one is -1/1 for your slope, x plus 0. 1/1 x plus 2. There's your slope and your y-intercept. So start at 0. Down 1, right 1, down 1, right 1. Start at 2, up 1, right 1, up 1, right 1, just in case we got some brain farts happening. Number 2, anytime they just have a line like that, you've got the line y equals 3, y equals -6. Those are perfectly horizontal lines, just like we did for number 5. Okay, so if you're forgetting those, the reason they were at the top of the assignment is because they're a little bit easier to do those straight lines. Okay, they're not easier if your brain is farting though. And it's like, well, how do I graph? What's the chart for this one? There is no chart because they're just straight lines. All right. Anything else I can help you on? Nope. We good? Marvelous.